Hello, everybody. Today we'll be talking about precise control and adaptive role management of robotics. My name is Michael Muldoon. I'm calling in from Montreal, and I am the sales director and director of product development at BBNR, where we developed precise control systems for finishing and visual inspection. And additionally, I'll be talking about command robotics, the adaptive role management platform that I developed and deployed, which is responsible for higher order level tasks and deployment to many robots out in the field. Precise control robotic systems. So these would be more the traditional manufacturing robots where 6 axes and arms, so they're non-mobile. But we need to get to tolerances of 25 microns. So a robot itself is, especially these type of robots, are repeatable, but they're not precise. So what that means is if you have a robot and you teach a point, it can go back to that point within a very repeatable or accurate degree. Now, if you tell to move between 2 points, you'll get to those 2 points actually, but the path in between them will not be necessarily accurate. That's important for these type of systems, especially when you get into profiling and polishing any type of system that you want to use for altering the surface of the part because you're buying to the path. So there's many tricks that we developed to deal with them, and the control system for this was important. So we look at the overall architecture. So these finishing, what's what I call top automation. So you have many moving parts, have complex pieces or components that you're trying to manufacture that are very difficult to add complexity. You have many areas to control. You have spindles. I'll show you the video systems. So you're going to have spindles. You have use abrasives which wear over time. You have the robot itself. So there's many different aspects of this which all come together with many parameters, lots of data, and in the manufacturing world, you don't have a lot of time. You make your money by manufacturing components. Therefore, you got to push those out of the field quickly. So the architecture that we use is revolved around the computer. So there's a PC where Brainwave, which is the name of the software, resides, and we have a number of sensors. So these sensors are used for gathering data, taking measurements of a part that you may want to alter a robot plan. So Brainwave does all the computing, then it pushes to the robot the and parameters to execute, and the robot's in charge of everything that's happening in real time. Okay, so all doors, all motors, all safety, it does the real-time control of this. Brainwave acts as the planner, and the robot is the execution system. I show a video of one of these systems. Let me just back up here. So within the system, this is the yellow robot. This is a Japanese robot by Fanuc. And the workpiece that we're working on is held by the robot. There's many components to the system. So you have a belt sander with 3 belt arms. So this is sanding. We use it to sand or change the aspect of the surface. Down here on the bottom corner is a polish spindle. You have many different types of abrasives, so you can tool change that. Here's a couple more abrasive wheels on this side. Here's your sensor system or your camera system. These are key-inch lasers. Up here, you've got a barcode reader, so you can read serial numbers and track data associated with that part. And on the end of arm, you have a couple features. Here's a diamond dresser. So this is used to shape these wheels. So you can imagine if we need to shape wheels to create specific shapes, maybe we're going to combine the process. We use the belt system for one aspect of the part, and we'll use the polish spindles for other aspects of the part. These are all, and we want to tie all this together to create one single finishing process. So during the video, you can see a little bit of the robot in action, and then I'll talk about the software architecture further. Here we're picking up the part, we're bringing it, and here's where we're using the abrasive to process the part. There's one other important element, just saw it quickly there, I'll back it up for you guys. So here, where this yellow sticker is, that's called a force feedback sensor. So what it does in 6 degrees of freedom, it measures the amount of force the robot is applying on a workpiece. And programmatically, we can control. So over a path, maybe we want to maintain a certain amount of force in a certain direction. So the robot will compensate to maintain force. So that's important because these components will often vary in dimension and shape. So we want to maintain a certain force across the surface. That's what allows us to give the robot a sense of touch. Okay, there's where we're taking laser measurement. This laser measurement is used to measure a feature and apply feedback to the robot path. Now I'll move on and show you a little bit of the software. So this software that we created, it centralizes all those parameters. It uses CAD to path, and we created a simulation environment to be able to teach all these parameters very, very precisely. So this is where combining force feedback, laser measurement, and precise teaching of the robot path, we're able to control and use these robot systems to be precise and create precise processes. So what we'll do is we'll break down this complex part into features. Each feature can have one or more elements, and then over top of that, each path represents a series of control points, and we can have specific control layers on each one of the control points. So here you can see we have acceleration, we have cutting speed, we have force, speed of the robot. So you can be very, I'll show an example here where we're going to apply a larger amount of force along a path. So here we're selecting the points. We're going to change the force applied from 20 newton meters to 40 newton meters. And what that does is it puts more force on the part, thereby removing more material. So you can imagine we could go point by point and very fine tune this recipe. You could have equations built in where you want to linearly modify, let's say, the force over time. So you could be very discerning on and very creative on your process itself. Now I'm going to talk about adaptive role management. So this is where you have a large number of robots, potentially a task-rich environment. So they want there's many tasks to do in order to complete a full-scale operation or just be productive. And we're generalizing the question of what do I do next? Okay, so as soon as a robot is available to do some work, you want to very quickly give it something to do so it's productive. Okay, so this is an AI goal system to build and deploy jobs to the robots, so you can share activities amongst many robots or have a single robot do many tasks. So we're really generalizing this. You can apply this to an environment where there's just one robot working, or you can apply this to an environment where there's many robots working. Now, the example I'm going to use, I built it around manufacturing. I did a case study around manufacturing, and there's a video that I have where it's just a test setup. But this can be applied outdoors. This can be applied indoors. This can be applied to a group of many groups of robots performing different operations. When I designed the system, I had in mind cost. So I wanted a single cloud-based platform that could be leveraged across many different applications. high mix in a variety of jobs. So one of the markets that I investigated was manufacturing. And typically when we think about manufacturing, we're thinking about um, large scale factories, but such as automotive. But the reality is that the majority of manufacturing is done on smaller uh, facilities. So they have high mix in a variety of jobs to do. Setup time has to be quick, has to be easy to use, has to be safe, and uh, has to allow robots to share tasks to be productive. So here is a video of the system in action. This is a setup I did in my basement with a company. So the hardware is from a company called Quantum Robotic Systems out of Toronto. And their robots, these particular robots, operate simply out of telemetry. So they're using encoders to track the position. So you can see the robot at the back. It does a little calibration before it takes off. And what I've done is create a series of paths and jobs, and I'm assigning the jobs from this cloud-based platform to the system. So if I just pause this, on the left here, this is the browser connected to Command Central, and here we have all the different workstations that I've built. And here is first robot and the second robot. This is their control system or their tablet. And you can see the second robot has a task assigned to it from Command Central, where it's to go from the infeed buffer to the basement test. So it's going to pick up this BB, so that's the label for the job to do, and it's going to move to infeed buffer, perform an operation, then go to the basement test, the destination, perform an operation. When it's complete, it'll tell Command Central I've done and ask what's my next task. So each robot is receiving tasks from Command Central. Okay, so to talk a little bit about the structure of and the architecture of this, so AGM, Adaptive Goal Management Command Central, it's an app which resides in the cloud, which acts as a fleet manager based upon an adaptive goal execution system. So what that means is a user deploys tasks, and since it's an adaptive goal execution system, as each task is being performed, it adapts and recalculates priorities. So a robot will be assigned an ID. That robot will pass the ID to the cloud, and along with a couple of characteristics, what type of task it's able to perform. And the execution system will look up, okay, what is, based upon calculations, what is the next optimal task to go after? And it'll respond back with some instructions. Okay, here's what you are to do. Now, I talked about safety. So this control system is really just a higher order control system. So all the decision making of what is done next is done in the cloud. And on the floor, the robot is responsible for executing those tasks. So currently there is no map. And there's a few reasons for this. It's more efficient. You can control more robots, and these robots can be in more environments. If I'm not worried about the map, I give that responsibility to the robot. So you could have many different types of robots. You could have wheeled robots, such as you see here. You could have drones. You could have bipedal robots, all working together to form with separate maps and separate control systems to perform getting work done. It makes it much more flexible. The way they talk together, there's a RESTful API. The robot itself is initiating the communication, and that's for security purposes. So you can imagine that the robot is maybe working within a network environment. So as long as it has outward access to the internet, it can ask for work. Um, the request always goes from the robot out to the cloud, and then the response comes back. So let's say that here's a manufacturing example. So let's say I want to manufacture this widget, and I have a number of steps that it takes, a number of different workstations potentially spread throughout the factory to get this done. So I've got a milling machine, I have a grinding machine, I have a CMM, which does measurement, and then I have marking. And then when it's complete, I have an area where, say, the shipping area, I call it out feed buffer. Okay, so the robot, this would be configured, all these steps would be configured in Command Central, and then the robot would ask, okay, what happens next? So in the raw part area, there's going to be raw part city. When the milling station's available, the robot will take it from in-feed to milling. And then once it's in the milling station, maybe it has an hour's worth of work. So then robot's available. What do I do next? Okay? It's always asking, what's the next job to accomplish? So that's where you can start sharing jobs. Or you could have multiple robots all working together to move the parts through. Imagine that while one robot's busy, there's other work to do. So maybe you want to have multiple robots working in an environment. I mentioned before, so since this is in the cloud, and the way I've structured it, you could have multiple facilities all sharing this. So think of a social media platform. The thing that makes it powerful is that you have many different people connected. Maybe you have many different Facebook pages where you have communities revolve around them. So my vision for Command Central was where you could have many different facilities being run off um, uh, one instance of this, making it extremely cost effective. In those situations, you need to really think about security. So encryption is very important in hardening of the system. Redundancy, by putting it into the cloud, you can leverage all of those redundant cloud systems for security and redundancy to really harden this software architecture. Additionally, the other benefit of having this cloud is you could enable revenue as a service. So this is one of my visions was instead of a robot, traditionally in a manufacturing environment, companies purchase robots through capital acquisition. So every year they plan a certain budget to improve their facility. And when they have a business case, they purchase the robot system, they implement it, make their improvement, and then run that robot. It's a typical useful life of a robot is 10 to 15 years. Every year they do a repeat. Where I had a vision where they could rent a robot essentially, and that helps them in a couple of ways. One, there's different budgets allocated for that. So you can access capital in different ways. Two, it incentivizes the provider of the robot system to make sure that that asset is always running, or else they don't get paid. So let's say that, as an example, let's say I want to get a haircut. So when I sit down, I'm not going to pay for my haircut until I'm happy, until I feel that the service is performed properly. And then I pay for my haircut. So I had a vision where the robot system would do the same. So when I move a part from one, say from the milling station, my example, to the grinding station, and it's done successfully, well, that robot has done its job properly, and then you can get paid. Okay. So my implementation of this was through a blockchain called Stellar. And on Stellar, you can transact in US dollars. And it was also very quick. So the transaction time was under 5 seconds to just completely settle the transaction. And I could also create NFTs or assets representing a robot. And that asset I could sell to somebody. So a distributor could own the robot and they could receive payments all centralized from Command Central. So that's my presentation for today. I hope everyone enjoyed. As you know, this presentation was recorded. So if anyone has questions, please submit them and I'd be happy to follow up and answer them for you. I hope everyone enjoyed and have a great day.